Hello again. So in today's video we're going to finish off just doing finite differences with Taylor series with another example. But the main topic of today's lecture is giving you a picture of numerical stability or numerical instability. Numerical stability is probably conceptually one of the hardest concepts in this part of the module, maybe the whole module. But once you've understood it with these examples, it's very useful. And you then sort of get a real handle on this topic. So I'm just going to hand over to the board and carry on there. Okay, so we're going to just do my final example, which is formula for first derivative now to second order. So the truncation error will be of order 8 squared in this case. So in order to do this, we're going to start with our two series. So we're going to have f of x plus h that will be this. And because we know that at the end it's going to we're going to divide through by h. We're going to expand up to the third order term because we're going to divide through by h eventually, and we think this will form the second order term. Now, it's note that I only leave the using the order notation until right at the end. The reason being is the order notation, whilst a useful sort of shorthand, does hide the sign, and if you're adding and subtracting lines of equations, it's important to keep the sign retained. So then we do f of x minus h, and this is just then all the odd terms go to negative sign, everything else remains the same. And then we think we want to get the f prime term. So to retain the f prime term, if we were to have the choice between adding and subtracting these two equations, we would deduct the two equations. So we call that a and call that b. We then do a minus b, and that gives us f of x plus h minus f of x minus h equals, and I'm going to write it down here. So the f of x terms cancel, the f prime terms come to h f prime of x, the f double prime terms cancel, and the cube terms go to h cubed on 3 f triple prime of x. So we're going to rearrange. So we're going to rearrange this and divide through by h. And that's going to be fine. So let's do that. So we then end up with f of x equals f of x plus h minus f of x minus h divided by 2h plus order h squared. So the h cubed term divided through by h gives you h term. So what we got is a second order accurate term. Now, given I'm conscious this is fairly revision from last year, I'm not going to go forward into other examples, but there will be a short part of the coursework which will be deriving a fourth order formula for either f prime or f double prime. And the trick is then, the higher the order accuracy you want, the more equations you start with. So you start bringing it in f of x plus 2h, f of x minus h. So often for fourth order accuracy, means using x plus h, x plus 2h, x minus h, x minus 2h. Okay, that's the idea. You build up your equations, and then that allows you the ability to eliminate more terms and remain with a larger term remaining. Of course, the result of this is the higher order accuracy you want, the more points you're using. Okay, so second order accuracy, you're using x plus 2h, x minus 2h. Fourth order, you're using maybe 4 points. And this is sometimes called something called a stencil, using an analogy of stationery cupboard. And this is second. Sorry. This is also called center difference, because you're differencing either side of x, and it's a very common choice of numerics in the sense that it doesn't use too many points, but also gives you second order accuracy. And second order accuracy tends to be quite a good working accuracy required. So I'm almost going back over this this sort of derivation to emphasize this thing called the truncation error, to emphasize what's called the accuracy of the problem. But then this gives us a lead in into the other side of the problem, which is the stability. And this is really where I want to get stuck into today. Now, numerical stability can seem a little bit abstract, a bit complicated, but it needn't be. And the way I'm going to approach it in this video is to give you a couple of pictures of how it works, okay, with an ODE. So we're just going to consider kind of simple ODE. So and the ODE was simply dx by dt equals minus lambda x, and lambda is a positive real constant. This is almost the simplest sort of ODE you can solve. It's a true solution exists, and we're using this example because there is a true solution, and that is that given if x at t is 0 is just simply called x sub 0, then x is simply, and we're going to call it x star, in fact, for the true solution, is x naught e to the minus lambda t. So what's the simplest solution you think of? So it's a solution that decays exponentially with time and goes to 0 as time goes to infinity, because lambda is a positive real constant. So let me just show this on this day. So there's x0, there's x, this is time, and then we have exponentially decaying, and this is our true solution. The reason I'm doing this is because we know unambiguously what the true analytical solution is, so we can start to understand this idea of numerical instability with reference to this true solution. So we're going to look at cases where the numerical solution follows the true solution, and cases where it doesn't. So the numerical solution, our time variable then goes to a discrete value of time, which is so n is a positive integer, and delta t. The delta t is called the time step, and we're going to basically divide up the time axis like this by chunks of delta t there, and it's positive. So delta t is greater than 0, goes without saying. And then we're going to solve this thing numerically. But I'm not going to show you how I'm going to do the details of the numerical solution. I'll just show you what it's like when it's numerically stable, what it's like when it's numerically unstable. Okay. I'm going to go back to the slides now. So where are we? There you go. So I was conscious, I've taught this type of material for quite a few years now, There's a conscious that sometimes the sticking point is not necessarily the maths per se, but it's maybe the concepts that come with numerical methods. And numerical stability is probably one of the most tricky sometimes, but once you've got a hang of it, then it's not a problem. So I'm going to start with a qualitative example, and then I'm going to go on to show a quantitative example for the next video. So I introduced this idea of shadowing. Now, if you don't like this concept, then forget about it. It's just my one way of trying to explain a difficult concept. So the idea is that when the numerical solution shadows the true solution, so it follows it. So if the numerical solution decays when the true solution decays, then it's considered numerically stable. That makes sense, doesn't it? As time goes to infinity, the numerical solution goes to zero. And shadowing is when the numerical solution decreases in the same way as the true solution. And I'm using shadowing rather than following because it could still have inaccuracies. It could still have reasons why the numerical and the true solution are separate. But if it's stable, then it both decays to zero. In contrast, when the numerical solution diverges significantly from the true solution, say it goes to infinity at time, and time goes to infinity, that's very common in stability, and then it's numerically unstable. So there we've got a very simple picture really of what can be a complicated idea, and that's what I say to come back to each time, and that's what I show in the next two examples where I've numerically solved for this e to the minus lambda t true solution for different cases. So here we're talking with the true solution and the numerical solution start at the same point at x is 1. The true solution, I've just shown it at every time step here, just for clarity, as these dots, and it decays nicely to 0 as time goes to infinity. Now a numerically stable solution will do the same thing. In fact, this is a reasonably accurate solution as well. It follows the true solution very closely, but I'm really mainly interested in the stability. And it goes to the 0 when the true solution goes to 0. So that's your first picture of shadowing of numerical stability. And numerical instability cannot be more different. And I use this right at the front on your LE page, I don't know if you noticed it, of a numerically unstable solution. It's like because it's such a key idea. And here the true solution is still decaying away nicely, very nicely, e to the minus lambda t. Numerical solution is going haywire. The first thing to notice is it's going to very large values as time goes to infinity. So it's what people often say, it's blowing up. When people say the computer simulation blows up, often they don't literally mean it's blown up. It's actually the numbers have gone out of bounds when they want it to behave, and this is an example of that. That's one thing. And the other thing is that it's alternating in sign as it's tending to infinity. So that's a sort of secondary feature, and it's not a feature of all numerical instability, but it's quite a common one. But the feature of it not shadowing, basically going off to infinity where the real solution goes to 0, is numerical instability. And you may notice if I was to cut this solution off at time as a half, it would look all right. It would just wobbling along a little bit, but then as time gets to 1.5, it starts to go out of bounds. And what happens is things like your round-off error, remember this round-off error that's very small normally, acts as a seed for numerical instability, and that's what the mathematical example that we'll pursue next time will show. It acts as a seed, and if there's any numerical instability in your method, it's going to act as a seed for growth of this numerical instability, and the solution corrupts. So I hope that's sort of breaking down this, trying to demystify this idea of numerical instability in the first time. Take a true solution and consider two examples, one numerically stable, one unstable, and what does it look like? And the contrast is very clear. And that's, if you ever getting worried about this concept, that's where I would catch. So this is a bit I've added into this course, in addition to what we'll do next time, which is sort of a numeric example. So hopefully the two things should sort of fit together. But you know, it might take time. It may be obvious to you, which is brilliant, but for others it may take time. It's my experience. This is one of the harder concepts. That's why I'm sort of making a big deal about it. Yeah, so that leads us with the sort of the final thing is that we've just shown some examples with Taylor series of different orders of accuracy. Just imagine you went through all the rigmarole and got a 10th order accurate scheme. Right, brilliant. You've done all the algebra, you've got nice differences. But actually when you run it, it's unstable. And that happens. So we need to be able to do analysis of the stability as well as the accuracy of these schemes. So you can have a 10th order accurate scheme, but it's of no use to you if it's numerically unstable for the situations you're looking at. And it can blow up. And it's arguable that numerical instability costs people who do big simulations, whether it be big astrophysics simulations or weather simulations, climate simulations, can cost a lot of money if you haven't got a stable simulation in the beginning. So this is where the mathematician really comes in useful, in that they can analyze the situation beforehand and give a guidance to whether a simulation is unstable or not. So it's sort of in bigger simulations it's a big problem and a big thing to get a handle on. Okay, so I'm gonna stop now because I think this is conceptually quite a big idea. Even though, so what I would advise before the next video is just looking again at these two pictures that are in the lecture notes as well, of course, and just sort of try and fix those in your mind as examples of numerical instability. Okay, and I'll see you next time. Bye for now.